All right, welcome to practice 3 for activity 6. In this example, we are going to be going through a paired samples, t-test, research scenario, and data set. And we'll calculate Cohen's d effect size as well as create a graphical representation between our two groups. So, our research scenario is a group of participants were asked to complete tests for determining VO2 max using 2 different protocols that were performed during 2 different sessions, 1 week apart in random order. Okay, so that's our methods. Participants performed the Bruce treadmill protocol, which is kind of considered our control group, in the lab, as well as a 2K rowing test in which their time was used to estimate VO2 max. You are interested in seeing if the 2K rowing test is just as effective as estimating VO2 max as compared to the Bruce protocol. So in this research scenario, we can pull out that the different protocols are going to be what we are primarily comparing. So that would be the 2 levels of our independent variable. And then what we're actually measuring, or our dependent variable, is going to be our VO2 max. Okay. We can tell that we have a within subject sample because we said that the participants were asked to complete 2 different protocols during 2 different sessions. So everybody has performed both protocols at least 1 time. Therefore, we should have 2 measurements per participant. Using this information, we're going to go through how the data should be organized in Excel and how that might help us when we transfer everything to SPSS. And then, assuming our data are normally distributed, we're then going to run a paired samples t-test in SPSS to figure out if there's a significant difference between the groups or not. Then we'll calculate the effect size, we'll make a bar graph. Similar to our previous independent samples example, I've given you guys the Cohen's d formula for a paired sample t-test, where M up in here is considered the mean difference, and SD is the standard deviation of the difference. So we can get this information from our output from the paired t-test in SPSS. All right, so let's pop over to our data set. And you can see we have our Bruce protocol VO2 and our 2K rowing test VO2 measurements. I've noted that VO2 max measurements are in units of milliliters of oxygen per kilogram per minute. And you can see the setup of this data set is quite different from the setup that we had in practice 2. Right? So in practice 2, we had an independent grouping of individuals where each individual was given a category. So gender, they had a label that said if they were male or female. And then they had 1 measurement that was listed for the dependent variable. In a setup for a paired t-test or for any repeated measures variable that we'll have from here on out, the variable itself will be indicated by the label that we place over the column. And then the actual data that's presented is the dependent variable. But remember that in SPSS, when we copy this in, each row is a subject, right? And so this would be subject 1, subject 2, subject 3, so on and so forth. And in our study design, we said that we have measured each subject twice. Once for the Bruce protocol and the other time for the rowing test. So this is what our data should look like when we copy it into SPSS if we have a repeated measure variable. So I'm going to copy this section and open a data sheet in SPSS, paste my variables. The confusing part for most students is that they think one of these needs to be nominal because we have a nominal variable. However, given the description I just gave you guys, right, each row is a subject number. So that means that each of these variables or each of these values in the table is actually representing a scaled variable or continuous variable, ratio variable. So that means each of our variables listed should be ratio variables. From here, we can use the transform and compute variable command to create our difference scores. That way we can assess our assumption. We're going to name our target variable difference. So we want to know the difference scores between our two groups. And in the instructions I gave you guys, I noted the Bruce protocol was kind of considered our control group, and we want to see if the rowing test is just as affected as the Bruce protocol. So our numeric expression should generally be the experimental group minus the control group. So we can just insert experimental group minus our control group, which is our Bruce protocol, and press OK. That should generate an output, or it'll say that it's generated an output, and what we're really looking for is the difference variable that's been added to our spreadsheet. So from here, we can then use an explore analysis, so analyze descriptive statistics and explore. The dependent variable we're interested in looking at the normality for is our difference score. So recall the assumption for a paired samples t-test is to have normally distributed difference scores as well as no significant outliers, with significant outliers being identified as greater than 3 times the interquartile range. So in here we're going to go to plots. We don't need a stem and leaf plot, but we just need the normality plots with tests. So this will give us our Shapiro-Wilk test so that we can assess our normality, and then it'll also give us our box plot so that we can identify if there are any outliers in our data set. So we can press continue and OK, and that will take us to our output. So now we have our explore analysis. I'm going to label this as practice 3 so I can keep track of my stuff. Alright. And then we can see some descriptive statistics for our variable. We could skip over those. The Shapiro-Wilk test, right over here, will tell us the p-value for normality. So based on this, the p-value is 0.709. And we typically say that the null hypothesis for the Shapiro-Wilk test is that the sample distribution of whatever variable we are looking at is normally distributed. So in this case, because p is greater than 0.05, we would accept our null hypothesis, and we would argue that we have normally distributed difference scores. So as far as normality of difference scores, I'd say we have succeeded in meeting that assumption. I'm going to get rid of the notes. We don't really need the case processing summary, so I'm going to delete that too because I just want to get rid of things that we're not super interested in looking at, so that way we're not crowding our output. I'll also get rid of the descriptive since we're not looking at those. And then we're not looking at the QQ plot, nor are we looking at the PP plot, so those two can go. What we're interested in is the box plot and seeing if there are any outliers that are identified outside of the whiskers of our box plot, which from what I can see, we don't have any outliers, so I would say that based on our normality and outlier assumption for our difference scores, we have met the assumption in full, which is fantastic. So that now means that we can run our paired t-test, which we would find by going to Analyze, Compare Means, and Paired Samples t-test. Now we can identify the variables that we're inserting. I'm going to do my experimental variable first, so that would be my 2K test, and then I'll stick the Bruce protocol in second. Now, in the lecture video, I told you guys, if you happen to input these in a wrong order, which there really is no wrong order, if you click on the pair number for that cell, you can use this button here to switch the variables. Okay, so that's just so you're aware that exists. But once we put the variables in, we're pretty much good to go. We'll keep the estimate of effect sizes open so that we can cross-reference what we calculate in Excel with what we calculate in SPSS. But other than that, we're good to go. We can press OK. And then we can see our t-test has been added to our output. So I'll add practice 3 t-test in the side. I'll get rid of the notes. And then I'll label this practice 3 t-test in my output as well. We can see our sample statistics. So this is when we have our 2K and Bruce protocol values pulled apart from each other. And we can see the mean values, the standard deviation, how many people were measured, etc. We'll skip over the paired samples correlations. This is kind of an additional way that we can check if our samples or the people that we've collected are actually paired values, meaning they came from the same person, but I'm just going to cut this out because we're not going to pay attention to that. And then down here we can see my paired differences. So for pair 1, you can see that we've got the 2K rowing test minus the Bruce protocol, and that's how we end up with the mean difference. So this positive, because this mean is positive, that indicates that the 2K rowing test had a larger mean than the Bruce protocol. And if we look at the values up here, we can confirm that that is true. Okay. The standard deviation of the difference is 2.05. So again, we'll use these two values to calculate our effect size. And then all the way at the end of the table, we can see what our p-value is for our t-test. So we have a p-value of 0.07. The null hypothesis for this t-test would have said that the protocols resulted in equal VO2 values, right? In other words, there's no significant difference between the protocols, or you could say there's no effect of the protocol on VO2. And if we evaluate this p-value in comparison to the alpha level that we used, which was 0.05, right? 0.07 is greater than 0.05. Therefore, we would accept the null hypothesis and say that there are no significant differences between the protocols for the estimated VO2. This would be one of those cases where you might say that a non-significant p-value is actually significant in meaning, right? Because if we wanted to validate this new rowing test as a way to measure VO2, and the Bruce protocol is kind of like the gold standard for measuring VO2. If we get reasonably similar results and they're not statistically significant, or they're not significantly different, then that validates that this rowing test likely estimates VO2 just as well as another protocol that has been used for maybe a longer period of time. So that's how we would interpret the p-value for our t-test. Just to give an idea of what we're aiming for our effect size, we have the point estimate value at 0.487 for Cohen's D. So while we're in here, I'm just going to come in to this table and copy the mean difference as well as the standard deviation of the difference. And then we'll minimize our SPSS stuff and head back over to the spreadsheet. So our mean difference and our standard deviation of our difference were represented by 1 and 2.05199 respectively. Okay. Cohen's D is going to be calculated per the equation that's in your instruction sheet and as well as your lecture. But we're looking at the absolute value of the mean difference. If you have a positive mean difference, you don't need to take the absolute value of it because absolute value function ensures that everything that comes out of it is positive. So we'll just do that divided by the standard deviation of the difference, and that should give us our effect size. Okay. So we see an effect size of 0.487. That coincided, or that agrees with what we got in our output. I would say this effect size is fairly close to 0.5, which is indicating that we have a moderate or medium size effect, right? So the difference between the means, which is a unit of 1 in terms of milliliters of oxygen per kilogram per minute, that, although it's not a significant difference, it is a medium-sized difference in terms of the variable that we've measured based on our sample statistics. So that would be how you interpret that. I would say let's create a similar table as we did for our previous example for the independent t-test. Oops. And this will just be so that we can insert this into a graph. I'll go back to SPSS since our mean and standard deviation were already calculated for us in the sample statistics. We can just copy and paste. So I apologize in the video, instead of zooming in and out, I'm just gonna paste everything in so that oh, and make sure that your values are in the right cell. So I just messed up on that. Control Z. I want my Bruce protocol over here and my rowing, or vice versa. Yeah. So when we look at Bruce protocol here, it's 52.88. The Bruce protocol in our output was also 52.88. So just make sure that you're not mixing up your values, otherwise you will get the wrong graph. We'll also copy our standard deviations from our output. Again, the first value that was listed was the 2K test, and the second value listed is the Bruce protocol. So from here, we can highlight our means and insert a bar graph. Okay, and from here, we might say this is the mean VO2 max estimates for, I don't know, different VO2 max protocols. I have my Bruce protocol and my 2K rowing test labels at the bottom. That's cool. And then in my chart design tab, I can add my primary vertical and horizontal axes. My vertical axis title is going to represent VO2 max in milliliters of oxygen per kilogram per minute. My horizontal axis is going to represent the protocol. And then I'm going to adjust my y-axis so that it's progressing by 0.5, just because I think that looks a little bit nicer. And then we can add our error bars. Again, the chart design tab, you'll go to add chart elements, error bars, more error bar options, which will pull up our toolbar where we can specify the positive error value to match our standard deviations, as well as the negative error value to match the standard deviations. And then, oof, we might have to change this again. Let's see. Let's do 1 larger than 1. Maybe 2. 2 looks a little better. Okay, just so your numbers aren't all like smushed up on the side, as long as there's like a decent amount of spread between them, I think you'll be fine. But this would be a nice example of what our graph would look like.